Alrighty, let's do another example. This is example 2, I think, from the classroom example printouts. And I'm going to use it as a way to explain the different ways of solving. So if you didn't see my previous video on the ways to solve, I did a brief summary on these 3 bullet points, which you should definitely see before looking at this video. Another thing that you want to maybe look at, if you haven't already, is properties of logarithms. I did a video on that as well. So I will be using properties such as, let me write some of them down here. I'll write them down, hold on. Alright, so those properties are properties of logs, properties of logarithms, such as the product rule, and I'm not going to write their names, I'm just going to write out the property itself. So a log base b of a product is equal to 2 separate logs, both of the same base, b, added so that each factor has its own log. It works that way for quotients as well, except that you will do subtraction here. And then we have the exponent property, and then we have the log base b of 1 is always 0, because any base rounded to the, any base to the power of 0 will give you 1, and also the natural log, or any log of any base, log of the same base of itself will equal 1, because if you take any base and round it to raise it to the power of 1, you will get back that same value. So those are the properties that I went over examples for in depth in a previous video. So we'll be referring to those. We'll have to employ those as we're going through solutions here. And so what I did in the video where I explained the 3 main ways to solve is just said that these 3 ways can work for depending on the form of the equation. And so you really kind of look at the equation and you determine which way you think is going to be most efficient, or the best way, or the easiest way. And so this one actually you can do with inversion or conversion. It doesn't really work well with matching. So I'm going to show you inversion and then I'll show you conversion. And I'm also going to show you how to do this with U-Substitution, because it makes everything so much easier. So first thing is I'm going to use conversion, and then I will show you the other way, inversion. So with conversion, what we do is we convert one of the, we can convert, let's think of this as the exponential and this as the answer. So if we want to convert that to logarithmic form, we would do the log of base 5, and then you want to swap the entire, you're going to swap this so that it's no longer with the base 5. It'll be on the opposite side of the equals. And this entire expression is going to be the argument of the log. Okay, so my log of 8 to the x plus 1 is equal to 2x minus 3. So that's the conversion step. I just converted from exponential form to logarithmic form. Next, I am going to what can I do with this? Oh, I know. I can use the exponential property. the exponent property. So what I'm going to do, switch back to blue, so I'm going to take this and move it in front of the logarithm. Alright, and then at this point I want to start using U-Substitution, because this is a value that I don't want to have to carry around. It's too clunky. And it can get confusing, and visually it looks more complex than it actually is. So I recommend you use U-Substitution. And this is the classical symbol. You know, this is the standard way that we use substitution in mathematics. We take the letter U and we let it be something. So I'm going to let U be whatever this value is. Right, so now I'm going to rewrite everything with my U in it instead of the logarithmic expression. And then it's much nicer and cleaner to work from here. So then I can distribute. I have U times X plus 1 times U is U. Now, it's important to keep in mind that you're solving for X, not for U. So you have to ignore U in the sense that it's not the letter you want to look for. Think of it as a number and focus on getting X isolated. So then we're going to move all the X terms to one side. So I'm going to go ahead and subtract so that'll cancel out. I'm also going to move the non-X terms all to one side. So I'm going to subtract U from here. Okay, so now I have to simplify this. I can simplify this as U times X. Let me use my blue. U X minus 2X is equal to -3 minus U. And then I can factor out the X, because remember, I am still focused on getting that X out. So I'm going to factor it out because I cannot solve for X if it's stuck in two separate terms. It needs to be alone. So I'm going to factor that out. And then divide both sides to cancel this out. And then evaluate by back substituting. So now I have X equals -3 minus U divided by U minus 2. So I'm going to back substitute my value. U equals the log base 5 of 8. And once you evaluate that, you can round it off to the nearest thousandth as we were directed to. Sometimes you're asked to leave your answer in exact form, so you do need to know how to do that as well. But sometimes, like in this case, you want to round it. So we're going to evaluate from here. Now there's a couple ways of approaching this. There's an incorrect way that will probably get you the right answer, and then there's a correct way that will definitely get you the right answer. And so I'm going to explain what I mean by that. So U, which is the log base 5 of 8, if I evaluate that using the change of base formula, it's equal to approximately 1.292. Now there's a lot more decimals that come after that, so I'm just going to, and 1.292. So this is an approximation at this point, because we've lost a lot of information. There's infinite number of digits that come after that last 2. So this is an approximation now at this point. And it gives us our final answer to be 6.062 when it's rounded to 3 decimal places. So that's our final answer, and it is correct. However, there can be times when you don't get the correct answer by doing this because of the round off error that's happening right here. And another reason that you want to know how to do it without rounding intermediary values is because when you want to check your answer, and you do want to check your answers in this section because logarithms have a restriction on the domain. They have to be positive. So there will at times be extraneous solutions. It becomes crucial that we always check our answers and eliminate any values from the solution set that would be problematic. And when you're checking your answer, you're hoping to see that the left side equals the right side when you plug in that value. So you can see that I've plugged in the rounded value, and my two sides are not equal, right? That is because of the round off error. When I use the true full value, not rounded, they are exactly the same. And you can see they're off by a lot here. Okay, so now I'm going to show you in Excel how you can calculate this stuff. Because I don't have the ability on the device I'm working on at the moment to open up Excel and demonstrate how to evaluate anything, but I can at least show you how I got my answers. So I will do a video showing you how I set this up, how to use it, how to make it, how to use it, or how to do it in a more simple way. I mean, this is a nice, neat, well planned out version. You don't have to be a professional to be able to do the principles that are shown here. So what happened is I made a place to input an argument and a base, and then using the change of base formula with a base 10 and with a base e, natural log, showed how you can arrive at the same correct answer, the same correct value, regardless of the base. And the reason we use log base 10 and the natural log is because every single scientific calculator will have a button for log base 10 and log base e. Not every calculator will have a function like this one, which is available in Excel. It allows you to specify the base. Not every calculator has that. So it's important to learn the change of base formula, and you will be tested on that. And the nice thing is that Excel allows us to check our answer in a more simplistic way for extra verification. So I like that. But you do need to know how to apply the change of base formula. But then I used it to get my numerator and my denominator. Let me get out of this. So I got my numerator and my denominator, and that was evaluating this numerator and that denominator, and then dividing the two. And so what I did is, instead of typing in the rounded value of 1.292, I was referring to the cell that contained the entire value. And it still gives me an answer that rounds to 6.062. However, then when I check my answer, I can refer, instead of typing in the rounded value here, I can refer to the cell that contains the full exact quantity. And then I won't have a problem like this. The two sides will be actually equal in that case. Video, I went in, all I used was conversion, though I did want to show you inversion as well. Yeah, so look at how many steps that was. Was this bad? Was it tricky? Was that something that felt horrible or just seemed like too long? It didn't seem like it to me, especially using U-Substitution. There's not, you don't have to keep rewriting this expression over and over again. Everything looks nice and clean. So conversion worked fine. Inversion will also work fine. So I'm going to show you inversion. So let's do that down here. Or was that number 1? I forget how I numbered these. Yeah, number 1 was actually inversion. So this was number 2, conversion. And number 1 was inversion. Alright, so inversion, let me write down and to do inversion, I'm going to do the inverse of raising a power, raising a base to a power. The inverse of raising a base to a power is to take the log. So I'm going to take the log base 5 of both sides, and looks like this. Alright, and this essentially does pretty much the same thing as conversion did. If you look back at that first step with conversion, we got something like this, but we didn't have a log on both sides. But the reason that it is pretty much the same process is because once I've done this, I can use the property to moving the exponent in front, right? And I can move the exponent in front of this one as well. And then what happens here is it equals 1. So now, I believe right here, we're at the same place as we were up here. Pretty much, yeah. So we're at the same place as right here by using inversion. So it actually, I guess conversion actually had fewer steps because we didn't have to simplify to get rid of that log on this side. It was already gone. So from there, the solution is exactly the same as earlier, as I mentioned. It's the same as that step I starred. So I guess I'll leave it there and do some more videos, more examples. I'll try to move more quickly so that you can see more. And what I'll do is I'll keep, referring back to these. And I think what I'll do also is I will, instead of numbering them, I'll use I for inversion, C for conversion, and M for matching. So I'll try to talk about, why I'm choosing a certain method depending on the problem as we go forward. So I'll see you on the next one.